Okay, thank you very much. It's really an honor to be here, and it's always a great opportunity to talk about the connection between meteorites and astrophysics, which is something that is a mission shared by myself and my co-authors. And we've seen in this conference already that closer star-forming regions provide more and more precise data than farther ones. And what could be closer than, of course, our own solar system? And a rock that you can hold in your hand. But of course the data is very different, and the connections are sometimes not easy to make. But meteorites have an exquisite amount of data to tell us and a story to tell. So today I'll talk about what they say about our sun's birth environment. So just for some background, meteorites are chunks of rocks that come from asteroids for the most part, and these asteroids could be melted or not melted. And if you have a meteorite from a melted asteroid, then we call it an achondrite. And if it's from one that didn't melt, and it still has the sorts of rocks and pebbles that existed in the solar nebula, you can hold them in your hand, then we call it a chondrite. And the chondrites have pieces of chondrules, they have CAIs, and the CAIs are especially important because these are the first objects to have formed in the solar system, and these are the primary way we know about the existence of short-lived radionuclides in the early solar system. We can date them using isotopes of lead, which form from the decay of uranium isotopes with half-lives of billions of years, but these also contained short-lived radionuclides that have half-lives up to tens of millions of years or much less. So after collecting and analyzing these, it's possible to figure out that aluminum-26, for example, existed in the early solar system. This is by far the most important short-lived radionuclide. It's one that has a half-life of 0.72 million years, and aluminum-26 decays to magnesium-26, and it's a positron. And it's always astounding to me that we can know 4.5 billion years later that this isotope existed in our solar system and even know how much of it there was. And the way we do that in the meteorite community is using mass spectrometry to measure isotopes in different minerals within single inclusions and develop an isochron, and that's depicted here. So a mass spectrometer, this one's at Wisconsin, is used to measure various spots within this CAI, this is a millimeter scale, and each spot you measure the number of magnesium-26, magnesium-24, and aluminum-27 isotopes and a number of atoms, and you plot them in this way with the Y being the 26-24 magnesium ratio and the x-axis being the aluminum to magnesium ratio. And the CAI was pretty homogeneous when it formed, so you would expect on a graph like this that all of the points should be in a horizontal line. They could have different aluminum to magnesium ratios depending on the mineralogy, but they should have the same isotope ratios. And yet, what we see is a correlation like this with a positive slope very often. And if you work through the math, it turns out the slope of this correlation is due to the decay of aluminum-26 to magnesium-26, and minerals that have more aluminum had more aluminum-26. And the slope of that line is the ratio of aluminum-26 to 27 when that object formed. And through these sorts of analyses, it's found that the vast majority of CAIs had a ratio of 5 times 10 to the minus 5, meaning that 50 out of every million aluminum atoms was the radioactive flavor. And that can actually be used as a times 0 in the solar system. When there was that much radioactive aluminum-26, that's when we'll call times 0, but I'll talk about that. You can play this game with many other radionuclides. Another very important one is beryllium-10, and beryllium-10 decays to boron-10, so you can measure the ratios of boron-10 to 11 and graph it versus beryllium-9 to 11. And I'll just use this as an example. You get the slope is equal to the beryllium-10 to 9 ratio, and I want to emphasize you always get a ratio of radioactive element to a stable isotope of the same element. And by looking at this slope, you can determine how much beryllium-10 was there, but we can also see what happens to these isochrons and what complicates the analysis. One thing is you might have a heating event, and the heating event might lead to a lot of thermal diffusion of atoms within the minerals, and you may redistribute all of those boron isotopes. And if that happens after there has been some decay, then what you'll see is that all of the isotopes are homogenized to this line. But then if there's any beryllium-10 left there, it will decay after that, and then you'll develop a slope. But it won't be as big because there wasn't as much beryllium-10 at the time that this formed. And so we have to distinguish between formation and later events. And usually what we refer to this as isotopic closure, when the atoms stop moving around. Maybe that was when it was formed and they never did that again, or maybe it was heated. Maybe it was aqueously altered and water moved atoms around, and that might lead to an isochron like this, and it may be a line or it may not even be a line. And with beryllium, beryllium is a very unusual element because it is so easy to produce an abundance of it through spallation. Energetic particles like cosmic rays hitting oxygen nuclei can generate this, and beryllium is pretty rare otherwise. So if you have cosmic rays spalling atoms in a gas or in a solid, you can create more beryllium-10, and you can even create a steeper slope that mimics the existence of beryllium-10, but it gets complicated. It's also possible, looking at isochrons of aluminum-26, to have a nice isochron, or maybe there was aqueous alteration or a heating event, and you only diffused atoms in one type of mineral. Anorthite is one that they're usually distributed in. But you could still look at these other minerals and have a slope from them and infer something about when the CAI formed and then also when later it was disturbed. So it gets very complicated and it is quite an art, but we can definitely determine how much was in these different, how many radionuclides were in these different inclusions at the time they achieved isotopic closure, whatever that means. And by playing these games with many hundreds of CAIs over decades, meteoriticists have developed a list of about a dozen short-lived radionuclides with half-lives up to 30 million years. And most of these were discovered by the time of the last PP6. One is new, curium-247. Evidence for that has come out in the last decade. But there's been updates to a few of these that are very important updates. One, beryllium-10 was discovered to have existed in the solar system back in 2000, but there were only a few analyses until the last few years. It's really exploded. Now there are dozens and dozens of beryllium-10 analyses. Iron-60 was one that was discovered in 2003, and it was thought at first to have a very high level, but it turned 10 to the minus 6 relative to iron-56. But it turns out that those first analyses were flawed, and more careful analyses of the isochrons with a lot more mass spectrometers, a lot more data, has pretty convincingly shown that iron-60 was present at a level of 10 to the minus 8 or so. And chlorine-36 is one where we've gotten more data about. I'll talk about that. So we have a long list of radionuclides, and we'd like to know a lot more about them. Now, why should we care about short-lived radionuclides? And there are a lot of reasons for this community to care. One is this is how we figure out when things happened. This is how we do chronometry. And you can get much more precise sequence of events using meteorites than through astronomical observations. And here's an example. This is a histogram of the aluminum-26-27 ratio in chondrules when they formed. And you see that the bulk of them have levels that are a few times 10 to the minus 6, something like 8 times less than that canonical 5 times 10 to the minus 5 that CAIs generally record. And that tells us that they formed 8 is 2 to the 3, so 3 half-lives later, about 2 million years after CAIs, assuming that chondrules and CAIs both formed from a reservoir with the same canonical aluminum-26-27 ratio. So actually, we can do very precise chronometry, but we always have to test this assumption that there's a uniform amount, homogeneous amount of aluminum-26 in the solar nebula, and we have to test that, which is something I'll discuss. This community should care about aluminum-26 because it's what melted asteroids. And by the way, it's not iron-60. It might have been important if it were at the higher value, but the lower value, it's not significant at all. Also, anyone doing MHD, short-lived radionuclides can ionize the gas, and where cosmic rays are shielded in the midplanes of protoplanetary disks, this is the dominant form. And since Hayashi-sensei is watching, I want to acknowledge that he considered the ionization of gas by radionuclides as well. In that case, it was potassium-40. But mostly, short-lived radionuclides tell us about the sun's formation environment and how it formed. And it's a remarkable story we recount in the chapter. The isotope, aluminum-26, and its half-life of 1 million years was only discovered in 1954. And months later, the great geochemist Harold Urey wrote a paper convincingly and rightly saying that that had to be what melted asteroids, the existence of that short-lived radionuclide, at about the abundance that we know it today. It was only discovered in 1976, the first evidence, but 2 decades before that, Harold Urey had figured it out. And he pointed out in this paper that the sun must have formed quickly because this is a very short-lived radionuclide. And as fast as the protostars in the Perseus cluster, which Blau had just figured out took 1.5 million years to form. So it's a remarkable marriage of protostars and planets that happened in the 50s and anticipated the correct result by 2 decades. But it did shape our conceptions about how short-lived radionuclides got into the solar system. So let's talk about that. There are 3 main ideas for the origins of short-lived radionuclides. One is that they could be injected into the sun's molecular cloud or disk at some point in time, and, or they could be produced in the disk by solar energetic particles hitting nuclei and transmuting them. And it's just also possible that they were in the molecular cloud to begin with. And I call these injection and radiation and inheritance. They're easy to remember. But because the short half-life is something that Harold Urey emphasized, I think for decades our thinking has been that you had to do something at the last minute to have it, and the inheritance was sort of underappreciated. We can test these ideas, and to make these tests we have to understand how they work and what they predict. So let me talk first about injection. And when aluminum-26 was finally discovered in 1976, very soon after, Cameron and Turin proposed the triggered star formation idea, that you had a supernova shock that both triggered the collapse of the cloud core and injected aluminum-26. And this model has been investigated quite thoroughly by Alan Boss and others. You could also inject it directly into the disk, which was a later idea, but one I worked on myself for a while. But it makes sense. We see proplids in the Orion Nebula that are in the vicinity of a massive star, and they can receive ejecta from a supernova or possibly Wolf-Rayet winds. I want to emphasize AGB stars and almost any other source, but a massive star has no place in this, although meteoriticists continue to think about it. But AGB stars are not associated at all with star-forming regions and young solar systems. But these models should predict that aluminum-26 and calcium-41, they might be absent in the earliest formed inclusions. Beryllium-10 would be different because it's not produced by stellar nucleosynthesis, so, but at least aluminum-26 and others might not exist. So at any rate, it would be very heterogeneous in the disk. That's the main prediction. Irradiation also predicts heterogeneous distributions. If you have solar energetic particles, protons, alpha nuclei accelerated in solar flares, they can transmute these nuclides as well. And there's some aspects of that, though, that make this a challenging model to make work. One is that you don't get to use very many particles. Most of the energy goes into ionizing gas. Something like 1 part in 10 to the 7 of all the particles can actually undergo nuclear reactions and produce aluminum-26 and beryllium-10. The other thing is, if you do create these nuclides, they're going to be higher concentrations near the sun and actually grow in time, according to one of the few quantitative models. But a very important aspect is that if you make aluminum-26 or almost any other nuclide by this mechanism, you will definitely make a lot of beryllium-10 because it's so easily generated by spallation. And so if this is an important mechanism, then you definitely predict heterogeneities, especially in beryllium-10. And then finally, inheritance. In the molecular cloud, you might just have stellar inputs in a sort of steady state way, contributing to molecular clouds over 100 million years in a spiral arm. And although it's not quite obvious, this also could explain beryllium-10. Because beryllium-10 is formed by cosmic rays spalling oxygen nuclei, and the cosmic rays come from, they're accelerated in supernova shocks. So you have high fluxes of cosmic rays where you also have a lot of stellar inputs. And so all of these radionuclides may exist in the molecular cloud and then just they could collapse and they could be inherited. And so these sorts of models predict homogeneity of the radionuclides. And it's very hard to keep them unmixed during star formation. Okay, so those are the predictions, and now we can see how in the last decade there's been a lot of progress towards testing these ideas and answering the origins of radionuclides. And I'll start with the irradiation model. And again, the big test is that beryllium-10 should be heterogeneous. And now that we have dozens and dozens of analyses, we can ask, is it homogeneous or heterogeneous? And it turns out, here's the compilation of all 60 now, some data, and they strongly, strongly cluster around a single value, beryllium-10 ratio of 7 times 10⁻⁴. And something like 90%, and even the exceptions are easily explained away. They seem to have been heated at a late time and giving them lower values, or they seem to have been affected by irradiation on an asteroid surface. And so there's a very, very strong peak in the distribution. So they look very homogeneous. And in contrast, one of these models, like if it were produced by irradiation, would predict that 50% of CAIs would differ outside of measurement errors from that peak. And so we just don't see that. And so we can conclude that irradiation contributes very little to beryllium-10 and by extension even less to the other radionuclides. There is a role for it, but not for the majority of radionuclides. So now we can test the inheritance model too. We can ask, do the other radionuclides look homogeneous like beryllium-10 does? And to do this, there's recent work. Actually, I'm going to present some work that I did, but this is in the field of chronometry. So imagine that you have a melted asteroid, and you have a piece of a melted asteroid called an achondrite. Because it was a rapidly cooled lava, all of the systems, all the isotopic systems should have isotopically closed at the same time. And so they should all of these different systems should record the same time of formation. The time of formation for aluminum-26 is found by comparing, the value you'd measure in a mineral in here to the solar system value of 5 times 10⁻⁵. But you can do the same thing for manganese-53 and hafnium-182. And you can compare these ages also to each other, but also to the lead-lead age, because you can measure lead isotopes in this as well. One obstacle to this is that these colored quantities here, these 4, are difficult to measure directly. We don't really know from measuring CAIs what the abundance of manganese-53 or 182 hafnium was. And as well, it's hard to measure the lead-lead age of CAIs. But if you knew those, then you could figure it out. So in this work, we took 14 achondrites, compiled all of these aluminum-26, manganese-53, hafnium-182, and lead-lead ages, and asked, could we make them concordant by just optimizing these 4 parameters, and make all of these ages be the same. And so the optimization using these statistical techniques shows that these are the optimal values and the range that provides a suitable fit. And these first 3 are actually very close to the previous estimates for these. So the half-life of manganese-53 is thought to be 3.7. 3.8 is probably better. And these abundances are about what could be measured in CAIs, but are a lot more precise. One difference is the lead-lead age of time 0. Like if you were to measure the lead-lead age of an object that isotopically closed at the time that aluminum-26, 27 was 5 times 10⁻⁵, you should get 4568.4. And that differs from measurements of lead in CAIs, which there's only 4, actually, 4 CAIs that have been measured. But this has been taken as the age of the solar system for a while. But this difference is easily explained just by recognizing that heating events can actually reset lead-lead at a late time and not reset aluminum-magnesium at an early time. So this age, saying that was the time 0, assumed something that hadn't been tested. This result that the solar system is about 1 million years older than CAI ages had been purported to be is also a finding by the recent paper by Perala et al. And once you have these optimized values, you can ask, does it make all the ages concordant? So on this graph, here's the time of formation of each achondrite, as measured in the multiple isotopic systems, and you can see, yeah, they match, they match, they match, they match. There's one outlier out of 38, and that has an unusual amount of tungsten for some reason, but this is as concordant as it gets, and chi-squared is 1.09. So this is very strong evidence. It could have falsified utterly the assumption of homogeneity, but it's very strong support for the homogeneity of aluminum-26, manganese-53, 182 hafnium, and of course beryllium-10 is homogeneous, and it can be shown also that iodine-129 was homogeneous. So the majority of radionuclides are pretty homogeneous, and that provides a strong support for inheritance from the molecular cloud. Now, as far as the injection model goes, it was motivated in the past by the true fact that there are some inclusions that have no aluminum-26 or very low values, including platy crystals of hibonite called plaques, corundum grains, and a few other rare and small, like less than 100 micron size inclusions. Hal has, that's hibonite in Allende meteorite, is an inclusion that has very, very low aluminum-26, 1,000 times less than CAIs, and you can't get that low by waiting to, and then resetting it, because you'd have to wait 7 million years. And it should already be in the Allende meteorite. And these inclusions also lack calcium-41. So this has long been taken as evidence for injection. This is an ongoing area of research, so I'm not going to overstate the case, but I don't think that these are indicative of a spatial or temporal heterogeneity. They are always associated with corundum and hibonite, always. And so it's more about a mineral chemical heterogeneity. There's something about aluminum-26 and calcium-41 that they didn't get into these inclusions, and I'd be happy to talk about that later. But let's just say the case for late injection probably has been overstated. Okay, so let's talk about the origins now, put it in an astrophysical context. Beryllium-10 is probably produced in steady state by cosmic ray spallation of oxygen atoms in molecular clouds. One problem with this model had been that lots of models had used the cosmic ray flux in the solar neighborhood to infer what level of beryllium-10 there should have been. And even if you multiply by a factor of 1.5 or 2 to account for the higher star formation rate, supernova rate, galactic cosmic ray flux, 4.5 billion years ago, you still got values that were less than like 2 times 10 to the minus 4. And of course, we saw it's at 7 times 10 to the minus 4. However, in recent work, it's been shown that the cosmic ray flux in the solar neighborhood is sort of an average for the galaxy, but the cosmic ray flux in spiral arms should be much higher because that's where all the supernovas are. Cosmic rays tend to diffuse for about 1 kiloparsec, and die off after 15 million years, so they are at a higher flux in spiral arms. And if you account for that, and this is a histogram of the cosmic ray fluxes that you would see, or the star formation rate in the local 1 kiloparsec, basically what star formation rate corresponds to the cosmic ray flux you see. This is the spatial distribution, so the average location, something like this, average location in the galaxy sees a star formation rate of 0.01 solar masses per year per kiloparsec. But the star formation rate in the nearest kiloparsec to a newly formed star is actually much higher. It's about 3.5 times higher. And when you account for that, that means that the cosmic ray flux in the molecular cloud the sun formed in, if it formed in a spiral arm, would also be much higher and totally consistent with the 7 times 10 to the minus 4 beryllium-10-9 ratio. This also means that beryllium-10 in the solar system provides a great constraint on the cosmic ray flux in the sun's molecular cloud if you're interested in doing astrochemistry. So beryllium-10, because it is from supernovae, galactic cosmic ray flux, is associated with spiral arms, but of course so are also aluminum-26, iron-60. This is a gamma ray map showing that the distribution of gamma rays emitted by aluminum-26 and iron-60 nuclei is concentrated in spiral arms. And this begins to paint a picture of how these radionuclides are produced and get into molecular clouds. So work by my collaborator Yusuke Fujimoto has done the hydrodynamical models, looking at the feedbacks between massive star formation and how they contaminate local clouds, and this feeds back into future star formation. And so I have a movie here. Let's see, I can get that to go. But you are seeing a local stretch of the galaxy spiral arm, and you're seeing the gas, and supernovas will explode in here and distribute radionuclides. And here's the star formation rate. So again, the things producing the radionuclides are near the stars that are going to receive them, and the molecular clouds that will receive them. And here's a map of where the iron-60 and aluminum-26 are going to end up. So, okay, thank you. So you have spiral arms as the site of star formation. If you account for this and make a histogram of what all the stars should form with, you see that this is the contour plot of the probabilities of how much aluminum-26 you'd have and how much iron-60 you'd have. And they tend to correlate because they both come from massive stars. The solar system values put you here. So it's kind of normal. It's pretty normal, actually, from an aluminum-26 standpoint, just slightly higher than the peak. It's actually a little low compared from an iron-60 standpoint. And this may be a hint that iron-60 is not making it into meteorites as efficiently as it is being produced. Maybe more iron-60 is staying in the gas phase. I'll come back to that question in a minute. How do the radionuclides actually get into clouds is an important question. And there's two models that we discussed in the chapter. One that's very intuitive is the punctuated delivery model. You just have supernovas, or you do have AGB stars, or you have other things that are contributing radionuclides at different times. And each type of event might be spaced delta T apart, and then after that event, you wait to form the solar system, this other delta T. And what these models need to predict is this ratio, the actual ratio, like aluminum-26 to 27, versus the production ratio that the stellar model would predict. And that is graphed here versus the mean life of the radionuclide. And these models predict this formula. And you can make this sort of fit. Short half-lives in a steady state thing are not as abundant. So these curves are more or less understood. But you need several types of stellar inputs, including one for the R process, one for the S process, and another recent thing, maybe a Wolf-Rayet star or maybe a supernova. And it doesn't quite even explain all of the radionuclides at that. A different type of model is sort of a box model in which you have a residence time of radionuclides in the diffuse ISM before they go back into clouds, which then form stars, but then of course the molecular clouds can disperse and put radionuclides back into the diffuse ISM. And by accounting for all of this, you get a different formula, which has different inputs, but these inputs are the fraction of mass that's in molecular clouds at any time and their lifetime, and these are pretty reasonable numbers. And then this one thing here is the ratio of inputs to molecular clouds from Wolf-Rayet stars versus supernovae. And these models are pretty successful at matching all of the abundances. Maybe not chlorine-36, but they do require that a lot more Wolf-Rayet wind material gets into molecular clouds than supernova ejecta by factors of thousands. Let me talk about chlorine-36 real quickly. The abundance of chlorine-36 is a little bit high. It's difficult to make it work consistently with chronometry. If you get into the detail of the handful of CAIs where it has been measured along with other things, including the Pink Angel, Curious Marie CAI, you find it's really kind of difficult to explain. However, chlorine-36 is only found in CAIs that have been aqueously altered at a late time. So a pretty good model out there, Jacobson et al., 2011, proposed that what you're seeing is that energetic particles from the sun are irradiating chlorine in the gas phase, and this chlorine gets into ices as hydrogen chloride, and then this gets into the asteroids and aqueously alters the CAIs. And there's a lot of consistency with that sort of model. But being energetic particles from the sun, they're easily attenuated. So this model only really works in a stage where the inner disk has been sort of evacuated. And I'll point out that we do think from a lot of other data that this was the case. There are no meteorites, chondrites that formed inside the orbit of 3 AU or so after 2.5 million years. So it's likely that the gas was absent and that the sun was a transition disk, and chlorine-36 appears to have formed during this stage. Okay, so to conclude, since PP6, there's been a lot more analysis of beryllium-10, updates to iron-60. We have a lot more aluminum-26, hafnium-182, manganese-53 data for achondrites, and lead-lead formation times have been revolutionized. So there's a lot on the data side. There's also been a lot more modeling to try to understand this and synthesize it. And the net result is that there's strong support for homogeneity of almost all the radionuclides. And therefore, inheritance from the molecular cloud is strongly favored. Evidence for late injection is a lot weaker than it used to be and may be absent soon, depending on how the modeling goes. And irradiation by solar energetic particles is all but ruled out, except, of course, for chlorine-36. That may be a viable mechanism for that. I think the future questions that we'll need to address are the following. It looks like chlorine-36 and some rare corundum hibonite inclusions are the only exceptions to the statement that we can do chronometry with the radionuclides. But we really do need to understand why it is that some rare inclusions that involve corundum and hibonite are lacking aluminum-26 and calcium-41, and really understand the collateral effects of radiation as well. It sure looks like beryllium-10 and separately the aluminum-26 and other radionuclides indicate the sun formed in a massive star-forming region in a spiral arm, and this means that probably most other solar systems would have similar abundances of aluminum-26, have melted asteroids, but it's going to be a lot of ongoing work to determine what do we mean by most and what do we mean by similar aluminum-26 abundances. And it looks like both supernovas and Wolf-Rayet winds contributed to aluminum-26 and iron-60 in the gamma-ray sense, but somehow Wolf-Rayet winds dominated over supernovas, it seems, in the radionuclides that ended up in meteorites. So it seems like there's something different about how material is injected from Wolf-Rayet stars into clouds versus how supernovas inject into clouds. It may have to do with the fact that supernovas occur from stars that are less massive, relatively to Wolf-Rayet wind star progenitors, and therefore have migrated further from their star-forming regions. So these are active areas of research, but I just want to say that meteorites are telling us many stories. Ask me later if you want to know what alpha in the solar system was, but the story they're telling today is that the sun formed in a spiral arm, and I thank you for your attention.
Thank you, Steve. Questions? Let's start here. Yep.
Lauren Weiss, University of Notre Dame. Great talk, Steve. Can you please go back to your conclusion slide? Okay, so what I'm, I guess, struggling to understand here is your statement or perhaps prediction that most planetary systems should have similar aluminum-26 abundances. And the reason I'm a bit confused about that is we are finding planets around stars that have formed in the thick disk and regions that are maybe not consistent with star formation or with forming in a spiral arm. Mm-hmm. So my question to you and perhaps to this whole room is, if it turns out that Wolf-Rayet stars and their winds are the primary driver of this aluminum-26 and iron-60 enrichment, what expectation should we then have about how this will affect planet formation in stars in different parts of the galaxy?
Yeah, great question. And so this is the histogram of what the models predict, and this assumes here that the injection of iron-60 and aluminum-26 in molecular clouds was equally efficient, which it may not be. I should have mentioned that Wolf-Rayet stars basically don't make iron-60. That's coming from the core collapse supernovae that comes later. But the Wolf-Rayet winds have a lot of aluminum-26 relatively. So this is the distribution, and what I mean by similar is this plot. You know, the solar system abundance is not, in an astronomy sense, that unusual, but of course it could vary by orders of magnitude. And Yeah, I think it's an important question to ask and answer. What fraction of stars form in high mass star forming regions versus even low mass stars? What fraction form in Carina, Orion-like systems versus, you know, the other parts of the disk? To answer that. But aluminum-26 it is what melted asteroids. It may devolatilize asteroids. That's an open question too. So it could be very important for those reasons.
Thank you.
Over here.
Łukasz Tychoniec from European Southern Observatory. Thank you for an inspiring talk. In some recent years, there's been a developments in how we see a dust growth occurring in the further away in the envelopes of the protostars as well. So I was wondering if there's any evidence. So one of the ideas for that is that we need to transport somehow the large grains that's forming the disk further out. And I was wondering if there's any evidence from meteoric tests to support that.
Yeah, the question of whether materials were transported is complicated. And I think that there are difficulties with transporting materials over the disk through a wind, but this has been invoked. There are, especially by Sasha Krad, who's observed some grossite, which is basically hibonite or corundum, grossite CAIs that are devoid in aluminum-26, but it's not clear why they are, if they were thermally reset or if they were lacking. So I can't really answer that in a short amount of time. It's a very complicated question.
Right, I'll find you.
It involves a lot of assumptions. Let's put it that way.
At the back there.
Shinsuke Takasao from Osaka University. I have a question about the 36 crew line. Could you show me the slide?
I'm sorry, the slide of?
Well, you mentioned the role of the solar energetic particles in the transition phase.
Oh.
All right, yes. So do you mean that only the CAI at the inner edge of the transition disks are irradiated by the solar energetic particles?
So in this model by Jacobson et al., what's happening is the solar energetic particles are irradiating the gas. Chlorine atoms are in the gas, and so at the inner edge of the transition disk gap there is the gas is irradiated. The chlorine there's chlorine-36, and that is efficiently trapped in ices. The ices are accreted by asteroids. The water melts, and the water reacts with CAIs. That's the sequence of events. It's pretty complicated.
Okay, thank you.
Over here. Yep.
Michelle Bannister, University of Canterbury. Could you comment a little on the degree to which the bias in the meteorite catalogue, being from a particular heliocentric radiance, and the degree of dynamical mixing that we've had within the solar system could influence this argument for homogeneity?
Yeah, great question. We always want more samples in meteorites, so I can say that we don't have a wide range. I mean, the ordinary and enstatite chondrites come from the inner edge of the asteroid belt, and the carbonaceous chondrites from the outer edge. CAI chondrites, which there are 5, may have come from 15 AU. They all show evidence for the same sort of aluminum-26, and so do the A chondrites, but it's a limited range. I would love to know what aluminum-26 was doing in the outer disk. There are some models, I don't favor them, but there are models that argue for different amounts of material falling on the outer disk from the inner disk with different amounts of whatever from the molecular cloud. So it would be a great test of that. What we do know is that Kuiper belt objects and comets, they don't seem to have had a lot of aluminum-26, but they must have some as well. And so some models constrain like their formation times. The Bierson and Nemo paper talks about porosity, and you need some aluminum-26, but not too much. So it looks like it's consistent with homogeneity, but yeah, that would be great to have more data.
So where would you want a sample from, ideally? Do you want an Oort cloud asteroid meteorite? Would that be the best test, or would you want it from somewhere else?
If you tell me where comets are coming from, then yeah. Yeah, cometary material, more CI chondrite, Bennu or Rugu would be great. Yeah. Okay.
Thanks.
Over here.
Hi, Adam Ginsberg from the University of Florida. You mentioned that cosmic rays come from supernovae, but recently there are models that suggest that there's enhanced cosmic rays during the star formation phase, possibly from shocks and outflows, or just more local to the YSOs. So does that have any effect on the models? I mean, you start with a steady state in the molecular cloud. Is there possibly local enhancement of irradiation over a timescale that's relevant that maybe you could test with some of the different ratios of irradiated nuclei?
Oh, thank you. Yeah, that's really interesting. So it doesn't change the conclusion that we need to form in a high mass star forming region, a spiral arm, but yeah, that's a definitely intriguing thing. The beryllium-10 abundance is sort of in steady state. It takes a few million years, just a few, to develop. So if these other anomalous cosmic rays are building up over millions of years, then they would be relevant, and that could change the numbers quantitatively. That would be interesting.
Over here.
Tristan Guillot from Observatoire de la Côte d'Azur, France, over here.
Ah, thank you.
The hidden microphone. I'd like to come back to this CAI chronology issue.
Mm-hmm.
Of course, I'm a bit disappointed because 4.567 was slightly easier to remember. But I'd like you to elaborate on this 1 million year offset. So, what do you envision? You said it's 4 CAIs that were measured
yes.
with lead
So
chronometry.
let me tell you the story. Thank you for asking that question. Yeah, this has been taken as sacrosanct for a decade now, and people forget there are only 4 uranium-corrected lead-lead isochrons for CAIs that have ever been measured. Connolly measured 3 and Emilie measured 1, and there's only one of those that simultaneously has an internal aluminum-magnesium isochron so that you can test this idea of whether they formed at time 0 or not. And nobody had tested that idea. So it turns out, and we demonstrated, that if you put a CAI, if you put that CAI in a chondrule-forming transient heating event with the same peak temperatures and cooling rates, that you will mobilize the lead isotopes and reset the age to start from that point. And you would not reset aluminum magnesium in any minerals except anorthite. And it turns out that the one CAI that has a lead-lead age that you can test, did it form at time 0, is the CAI SJ101. And it shows that the aluminum magnesium is not reset in the other minerals, but it is reset in anorthite, and it's pretty consistent with the idea that it just was heated at 1.5 million years after it formed, and you reset lead and you did not reset aluminum magnesium because that age was only using the other minerals. So anyway, that's it. It's a lot has been put on barely one CAI that is disturbed.
But so do you predict that other CAIs may have different ages, and that there was a spread in formation age, maybe?
Yeah, we would. They would have all formed at this time, but then they could have been reset by chondrule forming events, heating events, at random times, 1, 2, 3 million years after that. So we do predict that there will be a spread. But again, there's only been 4 measured, and the community needs, this is something I'm preaching to the meteoritics community, go back and measure more. We need statistics on this.
Yeah, thank you.
Thank you.
Over here.
Mark Crumhouse, Australian National University. I wanted to ask about your conclusion about the relative contributions of Wolf-Rayettes and supernovae, and how sensitive that is to uncertainties in the Wolf-Rayette production rates, because every time I look at that literature, I get frightened because there are a lot of assumptions in there, for example, about what the rotation rates are, about the treatment of rotationally driven mixing. So I'm just wondering how firm you think this conclusion is, or if you too are worried about uncertainties in the yield predictions from the Wolf-Rayette literature.
Yeah, great question. And Ed Young, my co-author, would have to be the one to answer that. But this parameter, 7,500, that's probably not right, but it's probably a big number all the same. And the basic reason is essentially Wolf-Rayet stars don't make iron-60. They make aluminum-26, and the solar system does not seem to have very much iron-60. So that's why the models are driven mostly, not entirely, but mostly to emphasize Wolf-Rayet material.
Okay, thank you. Over here.
Thanks. So Daraka from Jamstick Japan. So nice talk. So I have two short questions. So one is on the inhomogeneity observed only in abnormal CI. So not only plaques and fans, but also cometic condense and CIs are M926 free. Do you have any comment on that? So
Yeah,
on the original formation.
The inhomogeneity of aluminum-26, yes, there's plaques, corundum grains, some very hibonite and corundum-dominated CAIs, fun CAIs, but only if they're dominated by hibonite and corundum. If they're not dominated by hibonite and corundum, they have aluminum-26. The community has not done a good job at separating out all these things, so a lot of it's conflated. But probably I would need to talk with you in person, more detail.
Yeah.
Okay, thank you.
And, sorry, no time?
No time, sorry. At the back.
Takeru Suzuki from the University of Tokyo. My question is on chlorine 36. So most plausible production scenario of chlorine is solar energy particles after the inner disk is evacuated. If this was actually working, other isotopes will be produced. So my question is the quantitative consistency or inconsistency of chlorine with barium-10 or aluminum-26.
Yeah, that's a great question. Part of the complication is you not only have to produce the radionuclides, but get them into ice and dissolve them in water so that they can be taken to the CAI. I think manganese 53 would be one collateral radionuclide that would be produced, and that's worth investigating.
Okay, thank you.
Over here.
Hi, Abby Wagner, University of Virginia. So this question is concerning the solar-driven spallation that you were talking about, like this chlorine, and also with the oxygen. So can this process occur to other material, like, for example, sulfur? And if so, like, how much material is lost over the course of the planet-forming process?
So in terms of the transmutation of radionuclides, yeah, it could happen at this late stage. As we were just saying, it's complicated to see how you would see the signal because it's a little bit and it's happening in a late stage, and it's just that chlorine shows up nicely in the CAI, but others might not. In terms of loss driven by, I mean, yeah, there's a lot of UV that's going to go along with the energetic particles, and the UV is certainly contributing to the evacuation of the disk, but they are separate mechanisms. If I understand your question.
So like the oxygen 16 to beryllium 10, oxygen is being lost as a result of that. Do we have any idea how much oxygen is lost?
Very tiny.
Okay.
Very
Thank
tiny.
you.
Yeah.
Okay, over here.
Hi, I'd just like to, Mordecai Maclow, AMNH. I'd like to emphasize that there's a lot of quantitative evidence for the idea that Wolf-Rayets are going to be much more efficient at contributing mass. Lifetimes, Wolf-Rayets last 4 or 5 megayears, supernovae go for 40 or 50 megayears, clouds last 10 megayears at most, maybe 30 if they accrete enough, Mark. And also, if we look at the interactions of supernovae with dense gas, only 10 to 15% of supernova remnants actually show any evidence of interacting with molecular gas. Yusef Zada, about 2012, from the water masers. So there's all sorts of, and you know, theoretically, supernovae go off in associations, they form superbubbles. That's going to be hard to mix back into dense gas. And on the other hand, Wolf-Rayet winds interact with their predecessor red supergiant winds, as Garcia Segura and I showed many years ago. And so that's going to easily mix the ejecta from the Wolf-Rayet back into denser gas that can potentially be retained.
Oh, that's fantastic. Thanks for all that astrophysical evidence. And I would really like to see more connection between the meteoritic data and exactly that.
We may need to discuss this offline.
Yeah, sounds good.
Right, we have only 1 minute left. Let's squeeze in 2 questions, one from here, one from the back microphone, please. Okay.
Thank you.
Just
So
2 questions.
I'm Masaru Kobayashi from University of Cologne. And thank you very much for your review. Then I have a question how to distinguish the numbers of the Wolf-Rayet stars events or supernovae events, in a sense that this is somewhat related to the previous question. So we know from the theoretical point of view of the ISM dynamics, we know like clouds may have, say, a couple 10 mega years lifetime, or it could be 100 mega years. Then in that case, we have definitely several Wolf-Rayet stars or supernovae events, which means that they have a different production time, right? Then in that case, like those isotope ratio would be the superposition of those multiple events. Then can you comment on that? How can we pin down how many Wolf-Rayet events or supernovae events may be needed?
Well, yeah, so the amount of mass contributed by each is given by this ratio, and so the Wolf-Rayet to all sources is, in meteorites, again, is dominating. It's thousands of times the amount from other sources. What that means in an astrophysical context is more complicated, but...
Okay, we have that number there. Okay, let me check that.
Okay.
Yeah, thank you.
Final question, thank you.
Simon Porteries, Leiden Observatory. I have a question on the timescale problem of doing the Wolf-Rayet stars, doing the supernova, and injecting the material into the molecular clouds. You don't have that much time between the supernova winds and really putting the material into the disk, so to say. Would it be much easier to put it into a later stage and to have already the star cluster itself, where you have the Wolf-Rayet stars going off and the supernova and already the disk informing? But I mean, it would be nice if you can comment a little bit on this timescale problem.
So yeah, I'll start by saying that I gave up on the injection into the disk problem because timescales don't work out. You need the earliest stage of the disk to receive radionuclides, but it's the late stage of even a massive star is 4 million years, and so they are necessarily parsecs apart, and it just doesn't quite work. One of the aspects of this model, Ed Young's model, and our general picture is that you're constantly putting stellar inputs into molecular clouds or into the diffuse ISM and molecular clouds, and then they're mixing, and because this is all happening in the spiral arms and it can happen over hundreds of millions of years, you slowly build up this steady state abundance. It kind of obviates some of the timing issues, but not all, so I'm just going to have to leave it there and say it's very important questions.
Okay. Well, before we all go to lunch, first of all, there's going to be an announcement from the LOC. But before we have the announcement, let's thank Steve again.